Hello there. In this video we're going to be discussing some important properties associated with logarithmic functions. So recall, at least for some previous videos ago, an exponential function and its transformations can be expressed as a multiplied by b to the power of x plus c, and a logarithmic function is going to be, including its transformations, equal to a times the logarithm base b of x plus some c. Alright, so what I want to do first is just describe a couple little transformations on these functions that may be useful in a variety of applications. The first example I want to look at is exponential function. So let's assume we have a function of the form 3 times 4 to the power of 6x plus 2. Now notice here I have a constant next to my variable, but in our original form we do not. So sometimes it's important to express it in this form or vice versa. So using our properties of exponents, we have that this is going to be equal to 3 times 4 to the 6, all raised to the power of x plus 2. Now notice here that pretty much we're in the form that we originally stated. So this is pretty much in the form a times b to the power of x plus c, where a is equal to 3, c is equal to 2, and b is equal to 4 to the 6th. This is a common transformation that is used with radioactive decay problems, which we'll discuss a little bit later on as well. So a similar analysis can be performed on logarithmic functions. So let's assume we have the function, let's see, say g of x is equal to 5 times the logarithm base of 2 of 3x plus 7, right? So let's see if we can transform this so that we only have an x on the interior of our logarithm, right? So we can rewrite this using one of our properties of logarithms. So remember that the log of the product is the same as the sum of the logs. So this is the same as the log base 2 of 3 plus the log base 2 of x plus 7. And then we can distribute and then reorganize. So this is the same as 5 times the log base 2 of x plus 7 plus 5 log base 2 of 3. Now keep in mind that this expression at the end is just a constant. Therefore we have that a is equal to 5, c is equal to 7 plus 5 log base 2 of 3, and the base of this logarithmic expression is going to be 2. And again, this transformation is sometimes obvious or sometimes useful to sort of reorganize or restructure this logarithmic or exponential function for analysis, depending on the application. So in general, a basic logarithmic function is of the form log base a of x, right? So what is the domain and the range of this particular logarithmic functions? So remember that the domain of this function is going to be equal to the range of its inverse, which is an exponential function, namely the range of a to the power of x, right? So remember that the range of this was 0 to infinity, so that's going to be the domain of this logarithmic function, and the range of f is going to be equal to the domain of its inverse function. And remember, the domain of a to the x is the set of all real numbers, or an interval notation, minus infinity to infinity. And in order to graph our logarithmic function, right? So remember, the inverse is our exponential function with a horizontal asymptote here, right? So this point is 0, 1, so this is f inverse. So our function of interest is going to be this curve. So this point is going to be 1, 0 with a vertical asymptote at x is equal to 0. So this is the graph of f, right? So that's the graph of the basic logarithmic function for some base a. So let's work through a brief example on how to graph transformations of logarithmic functions. So let us graph the function t of x is equal to 5 times the logarithm base 2 of x plus 3 plus 1. So just by looking at this curve, pretty much this is a horizontal shift to the left 3 units, and this is going to be a vertical shift up 1, right? Now up 1 doesn't really look that much different because it's still going to cross the x-axis on the positive side of something, and the vertical asymptote is of course going to shift a little bit. So if we focus on this horizontal shift portion, so the vertical asymptote, x is equal to 0, is going to shift to the left 3. So that means this is going to move to the point x is equal to minus 3. You can easily see that if you look at the inside of this logarithm, because negative 3 is the value that makes the interior equal to 0, right? Now, if that is the case, I'm also going to find out where it crosses this value. So it's going to cross that point, or I'm going to try and find out where that point is shifted to, when the interior is equal to 1. So x plus 3 is equal to 1 when x is equal to minus 2, right? So that means the log of negative 2 plus 3, which is equal to the log of 1, is going to be equal to 0. And that's, of course, true for any logarithm, in particular base of 2, right? So we're just gathering some information before we go into this graph. All right, so let's plug in this point negative 2 into our transformation function. So remember, t of x is equal to 5 times the log base 2 of x plus 3 plus 1. If that is the case, that means t of minus 2 is going to be equal to 5 times the log base 2 of negative 2 plus 3 plus 1. Remember that this is equal to 1, log base 1 of 0, that is equal to 0, and this is just going to be equal to 1, right? So that means the point negative 2 comma 1 belongs to the graph of t, right? So that's an important piece of information. So let's begin graphing this. So remember, we have a vertical asymptote at negative 3. So let's begin by graphing that. And we have this point negative 2, 1. So if we graph negative 2, 1, so 1 is up here. So it's going to pass through this point, and then we can extrapolate all the other values, right? So that is pretty much the graph of our function t, right? And this is going to be our x-axis, and this is going to be our t of x-axis. Great. Now we can find out this x-intercept if we want to, but we'll leave that question later when we learn how to solve logarithmic and exponential equations, which will be in the upcoming videos, of course. Now, another important thing to notice about the logarithmic function, and I'm going to use the natural log just as a basic example. Remember that the natural log of 1 is equal to 0, or the log, any base, is equal to 0, right? So if we graph our logarithmic function, so this point that I'm referencing is right here. Now notice that it's negative if my x value is in between 0 and 1, and it's positive if I choose a value that's on the positive x-axis. So this is very important, and I leave it to you to verify algebraically. So if I have the natural log of x, this is going to be positive for any value x that is bigger than 1. The natural log of x is going to be negative for any value x between 0 and 1. And as we said above, the natural log of x is going to be equal to 0 for x is equal to 1. So that is the different cases for logarithms. Or you can say the natural log of x is undefined. Undefined in R for any x less than 0. We can talk about this when we discuss the complex plane in more detail. But moreover, the natural log of x is undefined, both for R and in the complex plane for x is equal to 0, right? So those are the 5 primary cases, with the primary most used cases being the first 3. So a basic example of this is the following inequality. So my goal is to solve the natural log of 1/4 x is greater than 5. Now, you may be thinking, oh, I don't know how to solve logarithmic inequalities. Well, notice this is not a logarithmic inequality, this is a linear inequality, because natural log of 1/4 is just a number multiplied by x to the power of 1. So this is a linear inequality. So remember from the property above that 1/4 is in between 0 and 1, which means the natural log of 1/4 is a negative number. So when I divide both sides by natural log of 1/4, since I'm dividing both sides by a negative number, I need to change the sign of my inequality. So that means x must be less than 5 divided by the natural log of 1/4, right? So if I want to write this in interval notation, that means x must belong to the interval minus infinity to 5 over the natural log of 1/4. Now you could approach this in an alternate way, and let me sort of show you how to do it another way. So again, we have natural log of 1/4, x is greater than 5. What I can do is I can apply my properties of logarithms on this natural log of a quotient, which remember is the natural log of 1 minus the natural log of 4 times x is greater than 5, right? So remember the natural log of 1 is 0. So we just have the negative natural log of 4x is greater than 5. And then we can divide both sides by natural log of 4 if we want to, right? And we know that natural log of 4 is greater than 0 since 4 is greater than 1, right? So then we have minus x is bigger than 5 over the natural log of 4. And then we can multiply both sides by -1, and that will flip our sign. So again, 5 is going to be less than -5 over the natural log of 4, which indeed is the same exact answer, just written in a slightly different, maybe preferable way. Right, so that's our solution. Alright, so now what I want to do is I'm going to look at a couple scenarios where we start mixing logarithmic functions with other function. So consider the following scenario. So let f of x be equal to x to the power n, where n is a real number, not equal to 0. And we're going to let g of x be equal to, say, the natural log of x. So question, is g composed of f of x always a logarithmic function? That is, when you compose a logarithmic function with a monomial, is it a logarithmic function? So we can easily work that out. So g composed of f of x, remember, is the same as writing g of f of x, and f of x is the same as x to the n. So we're going to plug in x to the n into our natural log of x function. So it's going to be in the natural log of x to the n, and then we can bring this power down, and we're going to have n times ln of x, right? Which is logarithmic, right? So this is logarithmic, right? So that's great. So the answer is yes. All right, so now let us look at another function, and let's see if we can find the domain. So find the domain of f where f of x is equal to the natural log of x minus 2 times x plus 3. So now we're composing polynomials with logarithmic functions. Now let's see what the domain of this is. Right. So f of x can be rewritten as the natural log of x minus 2 plus the natural log of x plus 3. And we can look at each of these pieces individually, right? So for this one, x must be greater than 2, and for this one, x must be greater than -3. So we simply take the intersection of these two. So the domain of f is going to be the intersection of 2 to infinity and -3 to infinity, which clearly is going to be equal to the interval 2 to infinity, right? So that's going to be the domain. All right, so also, let's consider this. So find the domain of g, where g of x is equal to the natural log of 2x minus 3 over x plus 4. All right, so similarly, g of x can be rewritten as the natural log of 2x minus 3 minus the natural log of x plus 4. So for the first piece, x must be greater than 3 halves, and for the second piece, x must be greater than -4, right? So the intersection of these two, so the domain of g, is going to be equal to 3 halves to infinity. Now you have to keep in mind, so caution, that this expression here is not actually the original expression. We have simplified it and or rearranged it. Now it is possible that both 2x minus 3 and x plus 4 can both be negative quantities if I choose a particular x value, right? Right. So question mark, is this the whole entire domain? Well, if I choose a negative number, like a negative infinity, for example, 2x minus 3 is going to be negative, x plus 4 is going to be negative, and their quotient is going to be positive, which is valid for natural logarithms, right? So let's do a more deeper analysis for this particular problem, right? So don't be too quick to assume, right? So g of x, natural log, 2x minus 3, x plus 4. So I'm going to define this to be equal to the natural log of y, right? So the domain of this function g is the set of all x values such that y is greater than 0, right? In general, that is the answer, right? And that comes directly from the definition of a logarithm, right? So we want to solve the equation 2x minus 3 over x plus 4. We want to find all of the x values such that this is positive. So what I'm going to do, since this is a rational function, is I'm going to perform a quick long division. So x plus 4 divided into 2x minus 3. So that's going to be 2 times x plus 4, so that's going to be 2x plus 8. And then I'm going to subtract those off, and then we get minus 3 minus 8. That's going to be minus 11, right? Therefore, this equation is the same thing as writing 2 minus 11 divided by x plus 4 is greater than 0, right? So what I want to do is I'm going to isolate this a little bit. So I'm going to have 11 over x plus 4 is less than 2, right? Or you can rewrite this as 11 over x plus 4 minus 2 is less than 0, right? Because this is our normal rational function simple transformation, right? So remember, y is equal to x has this function, right? 1 over x, I mean, right? So the transformation performed were left, so left 4, and then down 2. So if I graph this function r of x, then I'm going to have, so I'm shifting down 2, so 1, 2, and I'm shifting to the left 4, so 1, 2, 3, 4. Right? The coefficient on our thing is positive, so therefore we're in the quasi-quadrants 1 and 3. So I want to know when this curve is negative, so I clearly see two intervals. This interval right here and this interval right here, right? So clearly we're going from negative infinity to negative 4, everything. So those are some of our negative values that work. And also there's this x-intercept to positive infinity that is going to work as well, right? So we need to figure out the x-intercept, and that's easy to do. So x-intercept. So we just need to solve when is 11 over x plus 4 minus 2, when is this equal to 0? So I can add 2 to both sides, multiply both sides by x plus 4. So I'm going to have 11 is equal to 2x plus 8. So that means 3 is equal to 2x, which means x is equal to 2/3, right? So this number here corresponds to 2/3, comma, just kidding, that should be 3/2. So 3/2. Right? And that corresponds to, remember, the domain that we claimed before, namely 3/2 to infinity, right? Which is interesting, and you can sort of think about why that domain that we quickly pointed to sort of is associated with this domain that we have obtained from our rational function analysis, right? So therefore, if g of x is equal to the natural log of 2x minus 3 over x plus 4, then the domain of g is going to be equal to minus infinity to minus 4 union 3/2 to infinity, right? So again, be careful. Do not use properties to transform this function into another function that may be easier to work with, because sometimes you may be sort of ignoring some of the properties of the function that you actually started with. Anyway, that's just some basic analysis and properties and characteristics of logarithmic functions. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.